ask. We are more than willing to kind of just weave your questions into our conversation here today. So we are following you for your questions on 2 different channels on YouTube. We have the DataStax and the DataStax Devs stream up over here for your questions. So I welcome them to come over. In addition to LinkedIn, I've got LinkedIn pulled up over here in the lower right-hand corner. So please, if you have questions, bring them on over, and we would love to make sure that we're gathering them as we go. So we are starting in Lucidchart today, and we're starting in Lucidchart so that we spend a lot of time setting up the problem. And we had an incredible review of our book and this process posted, I think, on the UK, Amazon, and then on Goodreads. Kind of not directly quoting, but it's a quote from Albert Einstein, where it's when you're addressing new problems, you spend a ton of time up front understanding them before you dive in and build them. So we really appreciate that incredible review that you guys have been posting out there about this. So thank you. And we're going to be following that today, spending a lot of time talking about the problem, outlining what it means to do pathfinding with different types of algorithms and different ways to understand shortest paths before we dive in and implement them in Gremlin with some really sweet sample data. So that's the tour of where we are. So thank you all so much for joining. And I see the Lucid charts are posted. So let's dive into chapter 8.
All right. So hopefully I've started these off nice and zoomed where everybody can read them right off the bat. So I pre-zoomed everything.
Nice. And appreciate that. So for those of you who might be new to this show or the Lucid charts, we open sourced all the images that we made for our book, The Practitioner's Guide to Graph Data. It's a book that I co-wrote with Dr. Matthias Brosheva. And David and I are going through this book, the entire thing, every week. And we have made it all the way from chapter 1. We're starting a new example this week in chapter 8. And as you all have already been picking up, it's all about pathfinding. This really beautiful intersection between graph theory, mathematics, theoretical computer science, databases, all this cool, awesome sauce. Anyways, so David, would like to start at the beginning.
Yes, Denise.
How familiar you are, what's your experience with pathfinding?
Other than what we've done here in this show and using path and simple path at times and, reading through the docs of what that actually means, nothing. So perfect. You get a clean slate, tabula rasa, and you get to build it up from there.
Oh my gosh, this is gonna be very fun. Okay, so absolutely. So with path and simple path, just to kind of recap, don't mean to keep putting you on the spot, but just like in your own words, what is path and simple path like from the Gremlin step? Like, what does that mean to you?
Well, a path to me would feel like the path going from one vertex to another vertex, right?
Yep,
and
exactly.
What is the path? What are all the edges and the other vertices that are in the middle between those? But it would be, I believe, like all of the paths, if you were to say, iterate over all of them,
yes.
As compared to like doing any kind of filtering or limiting, where simple path removes cycles, right? So there might be cases in a path where I would traverse back over a path that I've already traversed, but the simple path essentially removes those types of cycles, hence giving you a simple path to whatever the destination is.
Yeah, exactly. Perfect.
Did I get it right?
Yeah.
Woo! It's too bad right now. Alex and I were talking about this. In the next couple of weeks, I promise to have the second camera on again. So we can bring that back up. I did have my hands up in the air. I really was happy about that. Nice. You just can't see it though, right? You just have to hear from the voice. But anyway, okay, good. Okay, yay.
Yeah, perfect. So absolutely. So when we are using the Gremlin programming language, which is a language for traversing and walking through your data stored in a graph database, you use steps like path and simple path to kind of see the journey that you've been on. Once you finish a traversal, you say path, and it kind of shows you the full end-to-end journey of where you've been. Today, in the next series of episodes with this is going to be all about optimization. We're going to be diving really deeply into how do you optimize and find shortest paths. The shortest path being the fastest and probably the ideal amount of time that you would like your traversal to take. If you're going to run a path algorithm across your graph, you want the fastest result to be the shortest and come back ASAP. So the theme for the next few weeks is all going to be about optimization and how short you can make your paths, etc. So David, we're going to start at the beginning here talking about what it means to be a shortest path in two different contexts. We're going to talk about shortest paths just by their distance, like the number of vertices you go along the way. And then we're going to talk about shortest weighted paths, which kind of starts to bring us into our example of where we're going in Chapter 8, which is the Bitcoin network. And trying to decide, trying to decide if you're going to join one of these Bitcoin or cryptocurrency communities, how do you use the open source data about that community to decide if you trust somebody else? So,
that's interesting.
Yeah.
Okay.
That's
an interesting problem.
We're going to tie all of this together. So.
Awesome.
Anyways, so here's where we are. What you're looking at is just a basic graph. These are way oversimplified, but we'll apply them at large scale. So we see a graph, David. It's directed. You've got edges going from A to B, C, D, from B to C, and then from C to D, right? And so when you talk about shortest paths, like the idea is like, well, how quickly can you get from A to D? And I mean, that one's like super obvious, right? Like, what's the shortest way to walk from A to D?
There's a single edge between A and D, so I would probably walk that one.
Yeah, exactly. And so I think that's 8.4. That's the next tab over. Just kind of like over illustrating.
You want me to go to 8.4?
Yeah, that'd be great.
Oh, okay. I see what you're doing.
Yeah,
breaking it down.
Yep, breaking it down. One picture at a time. Yeah, I made a few extra live stream images just for our live stream audience today so that we can take it step by step. But yeah, so when we're thinking about shortest paths, we're just thinking about how quickly can you move from one piece of data to another, or from one vertex to another. And for those of you who may have just joined the live stream, we have links to the Lucid charts available. So just go into the comments and you can join and watch these as we go. These are all of the pictures and images that we put into the book that Dr. Matthias Brochler and I read. A few extras just for the live stream audience. So thanks for joining. But so that's,
by the way, I just have to say real quick, I just have to say this. So we have somebody who watches our stream, Raphael, that does a wonderful job of every week when we are in the live stream, ensures to keep his mouse out of the actual view. I think it's great, by the way. And so I appreciate, we can see that you're in there. But I know you can see him like move his mouse out of the way.
Oh, no, it's not a problem.
So it's all good.
Yeah.
It's all good. Yes, exactly. I think it's, oh no, I didn't mean for you to jump out. Oh no. I just killed our one Lucid Chart viewer. But anyway, no, I was appreciating the fact that you keep off the screen, so no worries. I hope I didn't just dissuade you from looking at it.
Yeah, no, please come back. Please come back to Lucid Charts. Anyway.
Yeah, come back. You can move the mouse around. You can draw it. Go ahead.
But anyways, no. So when you're thinking about that with shortest paths, and if we were to do like the paths, if we were to write a Gremlin code to walk from A to D, and you use the path step, we would get all three options. We'd get A, C, D, A, B, C, D, and A, D, right? Right.
You're going to get all of the paths that you could traverse.
Exactly. And so everything that we do in the coming chapters is going to be all about how do we only store the shortest. Like I want to walk through my graph and I only care that the answer was A to D. So just ignore everything else. That's everything we're going to be doing. So the other item to do is to kind of consider how this translates to shortest weighted paths, which is where we're going to go on the next few images. But I think you want to reshare those links so that everyone can get access to them. I don't know if that's what you're doing.
Yeah, I just saw somebody say the Lucid Chart folder is empty, and that's why I was looking over here to see if I could get a different link. It should be good. Let me.
I think if you right click on the public, is there a way to select a share option right there?
Oh, this here? No, not that. Whoops.
Yes.
Not that I was seeing. I mean, I was actually getting the link that I have.
Gotcha.
Let me try that again. Let me just see.
Okay.
I see you, Frankie. Here, try that, and let me know if that's still empty for you, please.
Yeah, and I think I'm wondering if the URL of the folder that you're sending over is not an invitation, so that's why it is yelling at you saying that you can't share it.
I'm wondering the same thing, and that's why I was kind of like going, is there a link or something else I can share here?
Yeah,
share.
Ha-ha. There you go.
I found it. I think, here we go.
And
thank you for recording that, by the way.
Yeah, just make sure it's read only so that we don't end up getting people edit access, if you don't mind.
View. It's view for public.
Perfect.
Yes. Yep. All right. Yeah, let us know, Frankie, if that one's better. Hopefully that one's better.
Cool. Thanks for sharing all those. I appreciate it. Because for some reason we still haven't figured it out. YouTube and LinkedIn will eat my eat my links if I drop links in the comments section. So
You
perfect.
you just need admin access is all. And it looks like Frankie is saying that's perfect. So it looks like that worked. Wonderful.
Great. Thanks, guys, for letting us know. So that's shortest path, right? So shortest path is just kind of context switching back to what these images are showing you. Shortest path is just looking at the number of elements that you have to walk through to get from your start to your end. So let's talk about shortest weighted path, because that's where it gets really fun with our Bitcoin network example. Okay. And I think that should be live stream 3.
All right. Okay, I see.
Sweet. So for shortest weighted path, the word weighted just means that we're going to start putting weights on these edges. And for this example, I want you guys to think about these weights as distances, like cities, and then how long the road is between them. And when you're doing shortest weighted paths, David, we're trying to figure out like what's the lowest cost. Like if you add up the weights as you go, what's the lowest cost that it takes to get from A to D? So
interesting.
Our old shortest path from A to D was to go direct, and that one has a cost of 10, right?
Right.
So can you kind of walk through there and see what's going to be the overall lowest cost path?
Yeah, it looks like A, B, C, D.
Right. And what cost do you get when you look at that?
6.
Yep.
It looks like a cost of 6. Yeah.
Exactly. So when we're doing shortest weighted paths, we now have to consider like a property or something along the way. And we have to kind of add it up and keep track of that as we go. And so that's what we're going to do when we do shortest weighted paths.
Okay, that makes sense. Okay.
Perfect. Well, that's even better. So what's really interesting is when we're doing shortest weighted paths in this context, we're going to be talking about a Bitcoin graph or a Bitcoin example, but we're going to get there in a second. So let's flip over actually to live stream 4. Okay. I think I just highlighted the example that you picked out in your head, David.
Okay, got it. Oh, yep, right, there you go. I see.
Yeah. So if you want the shortest weighted path, we're just talking about the minimum number of edges to go from one place or the other. And for those of you in the audience who have studied computer science or algorithms, there's 2 really popular ways that you walk through these graphs. And that's the image that we're going to get to on 8.5.
So these weights, I have an assumption I'm making in my mind is that these weights are going to have maybe something to do with trust or something like that later on. And that will help determine, even though there might be a shorter path to a particular Bitcoin operator or whatever person, there might be a more trusted path or something like that. Is it kind of where we're headed?
That's exactly where we're headed. And what I would like to do is, let's just talk about it now. It's a great time you brought it up. So let's not wait. So in this first example, when we were talking about shortest weighted paths, we were talking about distance, like distance between cities, right? Right. So like adding them up on the way, finding the minimum, that made sense. But in the context of the open source data that we all have access to, by the way, about some cryptocurrency networks, they had their users rate how much they trust other users. And this is the Bitcoin OTC network data that we're going to use. And it's available on the Stanford Network Analytics Project, or SNAP. So it's an open source data set. We walk through how to load it in the book. And if you're using the DataStax desktop examples for this book, we load it all for you, like that exact data set from Snap. But here's the deal. A high trust rating in that data set is 10. And a low trust rating in that data set is -10. So if I really trust you, I'm going to give you a positive 10. And if I distrust you and think that you are completely malicious, I'm going to give you a rating of -10. But we just talk about shortest weighted paths as adding up values and determining like a minimum value and then finding a minimum path. And
that's a little bit different. Yeah.
That's going to blow up how we do this, right?
Okay.
Right? So, because this weighted path here, I mean, if A trusts B with a rating of 2 and B, you can follow that. That's going to be the lowest trust value because it's, you added up the weights. But for our application, that also means that the path from A to B, B to C, C to D is a distrusted path.
Right. That, and if a rating of 10, positive 10, means you're the most trusted, yet the path from A to D, okay, that's a 10, but the path from A to C to D is actually 12. How do I know then at that point, like, doesn't that, I mean, okay, the rating scale is only 10, but if the higher number is better, that feels like that would be a better rating. So clearly we're going to have to do some work
yes,
to kind of figure this out properly.
Yeah. And so this is the beauty of graph data and bringing together computer science and ways people are applying it. Because this is something that Matthias and I ran into many a times when we were helping people around the world with their pathfinding applications.
Okay.
That the value of weight between the two things that were like determining paths between, the higher the value actually was better. And so we were actually trying to do like a maximization. You wanted to find the paths of highest weight. But for those of you who are listening and you're like coming from the math community, you're going, wait, that's terrible. Like we can't walk around graphs trying to find maximum weighted paths, because you're just going to walk around your graph forever and keep picking up more scores. And that ends up being like the longest path through your graph. So we're not going to get to all of that today, but throughout chapters 8 and 9, we're going to show you how to invert these scores. So we're going to have to do a little bit of data science, because we're going to have to flip the scores so that we turn a maximal problem into a shortest weighted problem, all while solving shortest path problems in Gremlin. That's a lot we're going to do over the next 2 weeks. So,
all right, well, let's do it.
Okay, so let's first talk about, so from, that was a great question. So for those of you who are kind of following that and your brain was kind of like, wait, what? We're getting into data science, we're optimizing, minimizing, just hold on that. We're going to get to most of that, if not all of it, in chapter 9. So that's where we're going over the next 2 to 3 weeks. Put a pin in it. It's okay if you don't get it for now, because we'll get there. But let's come back to doing the traditional shortest path problems, like when you're just walking from A to D and we're trying to figure out how you walk around your graph. And that's going to be called breadth first search and depth first search. And that's figure 8.5.
8.5.
Now, honest question, David. Before we just now talked about breadth first search and depth first search, do you remember ever going through this? Have you done BFS and DFS before?
Other than through this series, no. Okay,
awesome. So I love that, because you got to call me honest, because getting to work through these things is really fun for me. And I really hope that, I'm excited about this opportunity is all I'm trying to say. Really poorly, by the
way. see, Denise picked me for this because I have absolutely no knowledge of anything. So she knew so that's wrong, easily build it up from there. No, but truly, other than this series, I have not really gotten into DFS or BFS. No.
Okay, great. So DFS and BFS are just different ways to programmatically search through graph data, and it's like a fundamental process that you learn when you're kind of going through advanced computer science and algorithms. And it's just 2 different ways to get from the start, which is the green vertex on the top labeled start. And for those of you who might be red-green colorblind, I apologize. It's just the start vertex on the very, very top. And we need to explore all of these vertices to get to the end in red in the lower right. So what we're showing on the left is called the depth first search strategy, and the right is breadth first search. And at the end of the day, the difference is whether or not you're going deep first or wide. And for some of you who might have studied this, the difference in implementation is whether or not you're using a stack or a queue in your implementation. But let's actually look at it on the left. So all of the numbers on these vertices show you which vertex gets visited and in which order for the different algorithms.
Okay.
So on the left, we're going to start at the top at start. And when we're doing depth first search, we're going to first go to the vertex labeled 1. Exactly.
Okay.
And then from there, we're going to say, all right, let's go deeper into the graph. And we're going to go to 2.
Okay.
From there, you go to 3. And there's nowhere else to explore. So you go back up to 2.
Oh, that answers why.
Yeah. Once you've exhausted, you're like going deeper into the graph, you go back up. And then you finish those edges on your most recent.
I see.
Yeah. So then we're going to go to 4. And the only place to go after 4 is to 5, which you hit end at on your 5th step there. So that's the first time you found the final vertex was on step number 5. So
okay.
you've explored everything. Like there's no more edges to go to from 4. And so now you go back up. There's no more edges to explore from 2. Go back up. There's no more edges to explore from 1. So you go back to your start and you say, oh, there's an edge I've yet to explore.
Oh, okay. That answers that. Okay. I was wondering, I was like, wait a minute. If 5 is the end, then how do we get up to 6? So I did not realize you would actually walk right back up them and then go back to your start and come out from there. Okay.
Exactly. And so whenever you're doing pathfinding in Gremlin, this is what's happening under the hood. It's exhaustively exploring every possible edge so that you can get from where you're starting to where you're ending.
So I do have a clarification question.
Yeah.
When in a depth first search, when you have traversed down to the end of your first path, are you actually traversing all the way back up through the path to the start, or to then go down to the next path, or is that just kind of a way to illustrate it, right? To talk about it? Are you actually doing that, or are you just essentially moving back to that start object and then going on? Like you actually traversing back and forth?
You are not actually traversing back and forth. This was just an illustrative way to show it.
Oh, okay. Got it. Okay. Got it. Because I was like, wow, it's like, there's got to be a way to optimize that, right?
Right. And so under the hood, what's happening is a stack. So when you're using depth first search, you're using a stack. So you would put 1 on your stack, and then you would put 2 on your stack, and then you'd put 3. And 3 no longer has any more to explore. So you pop it off the top of your stack, and now 2 is there.
I see. Interesting. That's cool. Okay.
Yep. Right, and so now you see, now you would see that 2 has another edge. So then you push 4 on your stack, and you push the end on your stack, and you see that there's nowhere else to go from the end. So you pop it and you're back to 4. Nowhere else to explore. So you pop 4, you're back to 2. Nowhere else to explore, pop 2, back to 1. You pop 1, you're back to the start. Perfect. And then you do the same thing. You would put 6 on your stack, and then you see you can put 7 on your stack, pop or push end on your stack, and now you'd pop them all and be back to your start, and you have fully explored your graph space.
Okay. Now, one other question for clarification.
Yeah.
So
I love it.
When we're talking, Gremlin Traversals, I'm used to cases where if I have, say, a starting vertex and it has multiple paths, obviously depending on what I'm doing in my traversal, but if I have not filtered on anything or whatever, I'm saying just go everywhere. I expect that I'm going to have multiple gremlins that are all going on their paths in parallel, not in the serial fashion where I go explore one path and then I go explore the other path, something like that. So in the depth first search, that is really hard for me to say, by the way, depth first search.
First search, yes.
Yeah, I keep lisping it. In a depth first search.
No worries, I get it, same thing.
Again, the way that we're explaining traversing through the paths and that we're going through this path of 1 down to 8, and then we're going to pop back up and such. Are those actually happening in a serial fashion? Or do I have multiple Gremlin traversals that are traversing at the same time, and we're just explaining it one way or the other?
The latter. We have multiple.
Okay.
Every traverser is walking their own path, and I'm just kind of going back to some really, really early fundamentals of computer science to just kind of put a picture of how they're exploring the graph space.
Okay, thank you for that clarification.
Yeah.
Okay, got it. I think I'm on the same page now.
Yeah, and I'm sure that other folks had that question. So awesome question. Thank you so much for asking that one. And so at some point, we're going to dive into some really, really low-level Gremlin details to try and apply this concept to how Gremlin's working. But that's going to be once we get to writing the queries so that we know whether or not our query is actually the shortest path. So applying depth first search to Gremlin is coming when we get to writing our queries. We're still kind of setting up the problem. And I'm still monitoring questions over here on YouTube or LinkedIn. So please let us know if y'all have any questions. Happy to take them live. But I think what we just walked through with depth first search now can be contradicted on how breadth first search works. And you're probably guessing it in your mind. Oh, well, we went deep and this time we're going to go wide. And that's exactly the difference, right? So you can see on that start vertex, what you do is you put, now we're going to be using a queue in computer science, kind of going down into computer science, different data structures. When you're searching through your graph space, doing breadth first search, you're going to fully explore everything connected to the start vertex. So you're going to explore 1, and then you're going to also explore 2 into your queue. And once you have put every vertex in that first neighborhood in your queue, you're going to go to the front of the queue and you're going to explore its neighbors. So now we're going to go back to 1 and we're going to say, all right, well, what's connected to 1? And you end up going to 3.
I see.
And now we've fully explored 1. So we're done there. And we go back to 2 and we say, let's fully explore 2. And we find 4. And we're done.
Okay.
So now we go back to 3. It's like ping ponging, right? Now we're going to go back to 3 and we're going to fully explore what's connected to 3. And that's 5 and 6. And we're done. Go back to 4, fully explore what's connected to 4. And that's the first time that we hit the end. It's step 7. We're going to fully explore 5 and there's nothing to add. Fully explore 6. And that's where you find the 8th time that you will find a new vertex in the graph, and it's the end state. So that kind of is just conceptually the difference between how you kind of go deep first with depth first search versus fully exploring the neighborhood before you move on to the next level for breadth first search.
Interesting. Okay.
And so like the visual on the right-hand side, again, it's just kind of showing you the numbers in order of in which that search space is going to be visited. So you can kind of have an understanding of how breadth first search is different from depth first search. Thoughts? What are you thinking?
Well, yeah. So I'm noticing that the end vertex for path, I'll call it path 1, right? A little bit different in the breadth first search.
Okay.
We ended up getting to a different place, and I'm looking at this trying to, or is it? Or is it?
I was going to say, is it a different place or is it a different order in which we got there?
It's a different order. It's the same place. It's a different order. That's the difference.
Yep.
Okay.
Yep. Exactly.
I see now. Okay. I see. Okay.
Yeah. So
okay.
So the difference in depth first search and breadth first search is just going to be the order in which you arrive at, or the order in which you visit different vertices in your graph. Overall, when you're considering massive graphs, any type of graph, the amount of time it takes to do breadth first search or depth first search is the same. So, in this example, we got to the end goal on the 5th step using depth first search. And we got to the end goal for the first time on the 7th step using breadth first search. But when you look at the complexity of these approaches on average for large graphs, it's gonna on average take the same amount of time. So when you're starting at one place and employing one of these strategies, there's not a benefit to choosing breadth first or depth first in this brute force manner.
And we do have a question from our friend Daniel Kuppitz, who we all know.
Oh, great.
So the important question is, does Gremlin work in DFS or BFS?
Oh, see, now this is when Daniel's showing up just to trump me. So, Daniel, that is a great question. And we are going to get to that when we actually implement this with Gremlin. Because underneath, as you know, because you wrote the language, Gremlin functions more, well, Gremlin's a functional programming language. So it's talking about constraints that are pushing and pulling the vertices through your traversals. And for where we are right now in this episode, I don't want to go there, if that's okay. Because that's only going to make sense once we see the different shortest path examples that are coming up.
He's laughing.
Oh, I'm sure he is.
That's great.
Yeah. So I'm gonna sidestep that one, but come back to it, Daniel, because it's a really great question. But we're not quite ready for it right now.
Okay. And there is another question, actually. What is the advantage of doing BFS?
So algorithmically, they take the same amount of time. So doing depth first search or breadth first search, it's going to be the same amount of time. So I'm curious from an advantage perspective. I guess it just depends on if you really like to use stacks or queues under the hood. If you much prefer to use a queue when you're writing, you're going to want to do breadth first search. If you'd rather write and use stacks, you're going to want to do depth first search. But that's kind of getting down into the weeds of how they're implemented. And that really is one of the only main differences I can think of. But if those out here in the audience who have a lot of experience working with graph algorithms and graph data have a different perspective, I'd love to hear it. If it just comes down to stacks versus queues, that just might have to be the war that we have, right? So
it's like VI or Emacs, right?
Yeah.
Mac and Windows. Let's do it. There is one other question here real quick. I think this will be fast. Do arrows represent directed edges in the illustration?
They do. Yes, great question. And where are you getting these questions? Because apparently my feeds must not be up.
I'm seeing these on LinkedIn. Yeah, I'm getting them through LinkedIn.
Okay, well, apparently LinkedIn just doesn't want me to be able to follow the live conversation because I'm on it and I'm not seeing these. Sorry, guys. Oh, anyways. Oh, okay. I had to refresh and now it's back. All right.
Oh, okay. Okay, good.
Yeah, and Daniel just said, yeah, you're getting yourself on thin ice once you start talking about breadth first search, depth first search, Gremlin, and the internals. Thanks for that, Daniel. Thanks for just setting me up right there on that thin ice. And I said, nope, not going on to it. All right. So we've definitely way overspent a lot more time on this than I meant to, but hopefully now in your head, you can think about how you're able to walk through data procedurally in graph structures. Yeah. Okay.
Yes, so far.
So let's move on. I think, what do we do? 8.8 next? I think that's where we want to go. Image 8.8.
Okay.
Yes. Okay. So this is the type. So what we're looking at is an example of the data that we are going to have for the next few chapters when we're doing queries and talking about our data. It is going to be wallets on the Bitcoin OTC network. This is the public key version of that wallet that we're going to make available for this data. Again, the data is from SNAP, the Stanford Network Analytics Project. And the Bitcoin OTC network had their users rate how much they trust other users. So we're going to study user 1094 for a while. And user 1094, here's an example of their first neighborhood. They rated how much they trust these 5 other wallets that you can see here. So we're just kind of looking at the first neighborhood. And on the next picture, 8.9, we're going to kind of show you how you look at like a path between 1094 and its second neighborhood. Just kind of starting to look at paths to wallet 11 or 1334. And I think in the book, by the way, I don't know if you're going to believe this, David, but I promise you the following statement is true. I did a random number, I wanted to find somebody who is in the second neighborhood of 1094 for an example in our book. Okay. And I randomly just wrote a quick query to pick a random wallet, and it was 1337. I don't know. I thought that was very funny that happened. Like the first time I was writing this example. So the entire book, it's all about determining whether or not wallet 1094 trusts wallet 1337. And it was totally random. And I don't know if anyone's going to believe me when I tell you that was not planned. It just happened. But that's believe funny. Me or not, that's true. So here's how we kind of use these ratings. We're finding paths between 1094 and, just for this visual, 1334. And you can just see that there's 2 different ways that you find paths, right? So.
Right.
Yeah. And I think
right. I see a path between 1053 and 1334, and then 1173 and 1334.
Exactly. And I think the next image over shows two more paths.
Okay. Oh, okay. Yep.
So we're just finding different ways that you're going to be able to explore the space from 1094 over to different vertices that we care about in the result set. So just trying to understand the data, et cetera. And then I think the last one is 812. And again, these are all images.
Oh, okay. Did you want to see 811 or no?
Oh, we do want to see 811. Yes. Okay. Thank you for stopping there. So 811 is starting to show you how we're going to be using the stack operator to do weighted paths. And we're not going to get into the inversion of weights yet, because as we kind of talked about at the very beginning of this episode, to do weighted paths, we're going to have to do something to these weights so that we find shortest weighted paths. But for those of you who weren't here last week, we introduced the stack operator. And David, I don't know if you still have your satchel.
I do. I always have my satchel.
The satchel is back.
Should we show the satchel? Do you want to see it?
I find it very ironic that you exactly have this Gremlin's satchel.
Wait. Let's do this properly. I'm sorry.
We do need to do it properly. We do need to see David's satchel. But
and I need to get the chair out of the way. We're just taking a moment here. Don't mind us. And I got to be moving really fast, right? And have to be,
Yep, this is you. There you go.
Yeah, I can't. I'm sorry, I can't get the angle to get the whole shot of the Gremlin view in. But
just hold that for 1 second. I need a screenshot.
Oh, you're gonna take a screenshot? Is that what you're doing?
Don't worry, I got it.
Oh, did you get it? Yeah,
I got it.
Wait, I'm in the run. Here we go. What?
Yes.
Like, what are these people doing? I thought we were learning about Gremlin Traversals.
We are.
What's going on here?
About that satchel, because the way I like to think about it, when you're using with stack with the Gremlin operator, it is literally like you are having every Gremlin traversal start with a satchel, and you get to decide what you put in it. And for weighted path queries, we need to add up how far you've been, and we need to find the shortest values that are in these satchels or in the sack. So when we're talking about this, and I love that, that was so great. What we're really talking about is when you're writing Gremlin queries, you can use with sack to instantiate or to give every Gremlin a satchel. And we're going to be using sacks throughout these examples, and we're going to be putting values in them, like the number of vertices that you visit along the way, or what this image is showing you. It's adding up the weighted property on the edges of your graph so that we're able to calculate like the shortest distance that you're traveling. So your sack starts with 0. Then you visit an edge, you pick up the value from the edge, and you add it into your sack. And that's how we're going to be walking through this graph. So.
Okay. And just one thing to add real quick. So Daniel, by the way, he did give an advantage of BFS over DFS. Says advantage of BFS. You can leverage bulking. I'm sure Denise will get into that eventually. This actually makes it faster than DFS, especially when used on large, highly connected graphs. So it does sound like that, at least to Daniel, there is a benefit, right? Well, at least, I guess, depending on what you're doing, but it sounds like there is a benefit in BFS over DFS.
Awesome. Yeah, let's have a sidebar, and maybe we should bring him on. We talked about it last week. Maybe we'll see if Daniel.
Oh, yeah, we should bring Daniel on. No, totally. Okay, yeah. All right, got it.
All right, cool. Yeah, so I think if you all are looking at this example, if we're thinking about shortest weighted paths, on 812, we highlight the path that has smaller value because you're taking edges with smaller integers. And so all of these examples really are just trying to give you all a good mental picture of the types of paths we're going to be finding. So the path before had fewer vertices, so it was a shorter total number of vertices visited. But this path, it has a smaller weight because the last path weight was 10 and this path's weight is 6. So as you're exploring different applications of paths in your graph data, there's a whole world of ways that you want to think about how this matters to your end application and what you really want to be doing with your data. So,
okay.
David, any other final thoughts before we go over to the examples in our code?
So I actually do have one. Now that I should have realized this from the previous weeks, that you just simply use a sack to essentially add up the weights from all of the various edges in your paths and everything. Now, since we're using the scale of -10 to 10, I feel like that's not such a hard problem anymore, right? Because the sack is additive. If I have a -10 anywhere in that, I'm going to subtract that off. I mean, the lower number is worse, right?
Yep.
But I'm curious then, I'm trying to think about, and I wonder if you're actually just going to have an example of this, so I don't need to actually ask the question. I'm sure you do. It's the way you guys built this whole thing.
Oh, you're good.
But if I'm looking at a path like I see here, right, and I'm going to my first neighborhood, second neighborhood, third neighborhood to get to 1, 3, 3, 7, right? So I've got three parts to my path. And it feels like it's simple. In this case, it's 6. But let's pretend on one of those paths, let's say from 1094 to 1053, the rating was a -10. Well, at the end of that, it's very clearly going to be less than 6. Isn't that then my preferred path? Or the other one, then 6 is going to be the high number. For all intents and purposes, if I had the same number of individual paths in between my vertices, the higher number would be better, right? Is that it?
Yes.
That's all things being equal, right? The second you deviate and you have an extra neighborhood, or you've got a longer path, whatever the correct nomenclature there, it seems like that becomes a little bit more interesting.
Right. Okay. So there's a lot of beautiful thoughts that I just saw you had, and so I want to break them down, because absolutely where you're going is why this can be very interesting but very difficult at the same time. So let's back up. Which edge do you want to switch to -10 in your brain?
Yeah, let's just take 1094 to 1053.
1094 to 1053. So instead of that being 4, you want it to be -10.
Yes.
Okay. And on this example, -10 means you completely distrust.
Right.
+10 means that I trust.
Yes.
Okay, so if that means the path we're looking at now is -10 +1, so -9 +1, -8.
Right.
Okay, so the path now becomes -8, and the former path is 9 +1 +10. So now we're trying to think about, well, which one do you trust more? And here's where it gets hard, because when positive weights like 10 mean that you have high trust, and you're looking for the high, what we need to find in this application is a path of high trust.
Mm-hmm.
Because you want to say, does 1094 trust wallet 1337? And the only way we can understand, because 1094 and 1337 did not exchange Bitcoin on this network. So we have to look at the data to figure out if they should trust each other.
Okay.
So 1094 has a high trust relationship with 1268. And 1268 is like, I'm neutral, maybe trust a little bit, 1337. Okay. So like,
I see that.
Yeah, how do you reason about that to say that that path means that you trust them? And
that is. And if we, to that point, if we were to just make that path from 1094 to 1053, correct me if I'm off on this. If that was -10, that is, why would I even trust 1053's then rating of something else along that path? So it becomes a lot more interesting. So it's not just a simple additive math kind of thing.
Exactly.
Is what I think I heard you say. Okay, cool.
Exactly. It's not okay. It's not additive at all, because like in your mind, you just said 1094, I completely distrust 1053. And so like everything else that 1053 says, like I'm not even trusting it at all. It's no longer that the rating of 1 is kind of okay. It's that I don't trust that rating. So in math,
I see.
The difference between what you're doing is we're talking about adding paths, but how we apply it as humans is more like a multiple.
Okay.
So it's like your distrust of 1053 is so bad that it doesn't just kind of add on what 1053 has to say. It ends up becoming a multiplication. Everything that you're seeing and the complexity of how we do weighted paths, when the values of your data, you need to add them up and make higher, longer paths. That entire application is what we're going to get into in chapter 9, once we kind of have the basics underneath us on how to do pathfinding in Gremlin. And that's, so we're going to, but I love where you're going, because, and here's why. Let's pull this out, because maybe not everyone watching or, live or on their stream is like getting ready to go jump into the cryptocurrency community, but it's 2020. So maybe they are, I don't know. But David, I want you to think about it this way. We experience the pathfinding results every day on social media. Like every single day, when you're on Twitter or when you're on LinkedIn or your platform of choice, this idea of how much you trust somebody influences whether or not you accept like a new connection on a social media site. So let's just think about LinkedIn. And I can think about maybe some people who have reached out to me on LinkedIn because of this series. And here's what happens. You go to LinkedIn and you have an invitation, and it's someone that you're not directly connected with. But David, what do you look at first? Like if you've got a brand new person who's requesting to connect with you on LinkedIn, what do you first do?
I look at my friends. I see if they have any connected friends.
Exactly.
Yeah, it's the first thing every time.
Yes. So if that connected friend is someone that you work with at DataStax, how do you reason about the person who's trying to become your friend on LinkedIn?
Right. Well, if it's somebody if the connected friend is somebody who I know that works at DataStax, well, the first thing is they work at DataStax, so they automatically get some semblance of trust, right? Yeah. And then how well do I know that person from DataStax? And what do I know about them? So depending on what that answer is, then you kind of add or subtract from there, right? And then, of course, you look at the person and you kind of see what they're about.
Yeah.
Right? Are they creepy, or are they, or
yes.
what, or, so there's all these layers that get added on, and all of them are actually quite weighted now that I think about it.
Exactly. And they're all weighted positively in our brains. We talk about relationships and how strong your relationship is with your existing network. And the way that we humanly explain it, it's like Like the stronger my relationship, the higher the score I'm going to give it.
That's right. And it's funny as we break it down, like we use these terms like, strong, weak, or something like that. But now we're actually trying to take a quantitative measure of what that actually means. Yeah. That's pretty interesting. I hadn't thought about it quite like that.
Right. And so that, again, it's like another intersection of where things that we do so intuitively on common places like LinkedIn actually become very difficult to do mathematically when you try and implement them in graph data. And that's why I love this example. And the questions you're bringing up about like, wait, that was weighted -10 versus 10. I don't really understand how to add or how this is going to come together. I love that because it's showing me the connection between how this works in the real life, but then how we're going to do this in code. And we're going to have to do some pretty interesting things that you might not expect in order to make this work. So it'll be very fun once we get there. But
yeah, sorry. By the way, you can't see me, but I'm laughing right now because I'm reading some of the comments that are coming through. I don't know if you saw the ones on the YouTube channel.
I did not, and I'm sure
some of these are great from Kenny, and I saw a question also from Frank, our friend Frank, over in LinkedIn.
Okay.
And I think this is very relevant to what we're talking about. Do I have to rewalk the whole network if I update an individual trust level?
Oh, that's a really great question.
That is, right?
I mean, that's like the exact same problem. Like if you have a highway system and you decide to build like a super highway between two cities, how much do you recompute all of the paths that you know about optimal paths in your network? And honestly, that's a really great question. And I think the answer is going to be a little bit somewhere in the middle. Like you're probably only going to need to update your network for those paths which previously were using edges adjacent to that piece. If I were to have to answer right now, that's what I would say. I'm curious if someone else is thinking of a different way, because my brain was, I was like in a different train of thought in my head.
Frank offered up a really neat example, I think. He goes, this is like evidence from a crooked cop. Yes. You have to go back and re-examine all the cases that cop gave evidence for. That's a really neat analogy. I like that.
Yeah, and actually, if you would flip over to, I think, to this example, if you could go to image like 8.2, maybe 8.3, somewhere in the beginning. We didn't have it slated for today.
I was going to ask you if this ties into fraud detection stuff.
It does.
Yeah, it feels like it would.
It does. And so there, we've talked about so far. We've talked about logistics, how you use the distance in roads to optimize how you get from point A to point B. But absolutely, if you're an investigator and you're trying to paint together a story about whether or not someone suspicious is guilty or innocent, you're trying to paint together the story maybe of how they're connected to a crime or connected to another known criminal. And there's a really fabulous application that we've had the opportunity to be a part of here at DataStax that essentially implements this. For some communities, and I'm going to stop there before I get too far and what I'm allowed to not say. But anyway, but it's very fascinating to think about if you are trying to understand the connections between two people. Whether or not they called each other on a cell phone is going to have a certain strength or a certain weight to it.
That's right.
If they use the cell phone once, is that really a big deal? But that's a short path. There's a direct connection if these two people shared one phone call. But people share phone calls all the time. So is it a more trusted path to say that this person owns a digital account and these two digital accounts had a transfer event between them? It's a longer path by graph data standards. I'm looking at this image now, walking from suspect on the left to a digital account to a transfer event to another banking account to the criminal, right? So that's a path of much longer length. But maybe that's a stronger correlation that these two people are in cahoots than if they had one random phone call that could have just been a misdial or a robocall. You never know. So it's very fascinating to kind of take the human experience of how we reason about social networks and we reason about people and try and understand, what does trust mean between humans, and how do we quantify that in a graph database? And we've spent so much time talking about this. I don't think we're going to get to queries today, and that's okay. But this journey, David, is why I'm so excited about this next series that we're going to get to in our book example.
Yeah, and by the way, I was actually just thinking the same exact thing. I think we needed to walk through all of these to set up, and including for me alone, as you're bringing me through this, right? So for those watching and following along, I feel like we needed to kind of walk through this stuff so we can start getting through and making sense of what's going to happen in the traversals. Now, see, now you've gotten me excited too, because this seems like a really interesting problem to solve. And the cool thing is knowing how you guys built all this stuff out, not knowing what the actual traversals are, you did solve it. And it's presented in the book and it's presented here. So, this is stuff that's applicable in, I think, many different realms, right? It's no realms. I made it sound like we're doing like D&D or something like that, but Dungeons and Dragons, for those who didn't know what that was. But like, it's applicable to so many different types of problems that are out in the industry. Right. And so I'm really excited to see where we're going to go. By the way, I have to say that Kenny over on YouTube did say Denise adds more charm in this geeky routine. And by the way, Kenny, so I think Kenny's trying to set us up and did ask about a comparison between our graph stuff and Neo4j. And just so you know, like that's I don't mean to sound coy or anything like that, but that's not a comparison that we're here to make. So I'm just going to go, you can't, I keep forgetting you can't see me on camera. I make so many hand signals while I'm doing things. But that's, I would invite you to explore that one on your own without us going down that particular path here on the show.
Yeah, well, and I would say that it's a fascinating question, and we're experts on Cassandra, and we're experts on how to solve problems here. And we are so excited to invite you along the journey to learn how to solve the problem. And let us know what you find as you go to explore these on your own and try different options. Because the graph world is so vast and complex and beautiful, in my opinion, that I'm really looking forward to letting you kind of come to the journey on how we see it here. So I think with that in mind, David, in my head, I wanted to do two things, and I think I have time for both.
All right, we have 4 minutes. Let's do this.
The two things I wanted to do was to give you the answer we're going to get to at the end of chapter 9.
Okay.
And I wanted to also conclude with, because we've been talking a lot of theory about applications of it. I want to conclude with like a really obvious weighted example. So
let's do it.
So let's go to 8.3 on this image. I wasn't planning on talking about these, but we kind of went there. I think 8.3 might be what we want. If it's not, it's going to be 8.1.
Distribution centers, your home warehouse?
Yep, perfect. So this example, at the beginning of every chapter in this book, we spend a lot of time talking about how this application can be solved in different industries. So through the next few episodes in this series, we're talking about shortest paths, shortest weighted paths. And, through this awesome conversation, we kind of brought up how important it is to think about criminal investigations as shortest paths and understanding trust between known criminals and suspects. But this exact same way of thinking about it applies to how we do shortest paths for logistics, like getting a package that you just ordered off of Amazon from their warehouse to your home. Do they do a direct flight to a close distribution center? Do they drive a vehicle from the warehouse to a distribution center near your home? Do they do multiple flights or multiple vehicle transfers? These types of optimization problems are how these networks were determined. It's the exact same way you walk out your front door and decide how you're going to get to the grocery store or how you're going to get more gas for your vehicle.
And it depends on what the weights are, right? Do you want to take a scenic path? Yeah. And if you want to take a scenic path, you're going to have different weights than if you are stuck for time and you need to take the shortest path or something.
What time of day is it? How much traffic is on the road?
Yeah.
So there's the multiple optimization functions of distance, of time that you're going to spend on that route, in addition to your personal level of trust that the data and knowledge you have about them is up to date. And all of this comes together in pathfinding applications across any industry vertical. And after today, we're going to be really diving into how to apply this to exchanging cryptocurrency and trust on a cryptocurrency network. So if you are curious, download DataStax Desktop. You can look at all the examples ahead of time. You don't have to wait for us. But I am going to conclude with the answer we're going to get to in chapter 9.
Okay.
So we were looking at, I think it was on 8.12. we were looking at the second neighborhood between our person of study 1094 and our 1337. I think it was 812.
Yes.
Oh, I'm sorry. It was 889 or 810. It was back a few. I'm sorry.
Okay.
Yep. Okay, great. So in this example, for the rest of the examples, we're studying 1094 and we're finding shortest paths to, I promise it was random, 1337. And you can see here that 1337 is in the second neighborhood. So the shortest path by distance is always going to be 2. It's going to be going from 1094 to 1053 to 1337, or going through 1173. Shortest path by distance or by length, it's 2. We're going to go through global optimization heuristics and 2 other types of pathfinding heuristics for the A-star pathfinding algorithm to show you that the shortest weighted path has a length of 15 in this data. So if you want to apply how we're going to quantify trust and you want to go through the different global heuristics for doing A-star and Gremlin, we're going to end up finding a weighted path that's very long, but it's going to be the most trusted. So
how interesting. That sounds like fun.
That's where we're going. It's going to be
That's cool.
Probably the longest Gremlin query you've ever seen. I cannot stress enough how beneficial and awesome the partnership with Daniel Cuppets was, and Stephen Millett when we were writing this example. I could not have solved it without them, because they're amazing rock stars that I've absolutely loved getting to work with over the past 2 years when we were making this. So for those of you who are kind of watching the comms and you found Daniel, he's an amazing guru to get to know. Find him in the community because he's incredible. And I'm so glad he showed up for these. And we're going to have to find a way to get him on here to help as well.
Yeah, agreed.
So, all right. Well, that's it, David. We did a lot of chatting about examples, no code today, but we'll get there next week.
We did. I'll have to say, though, Denise, even though we pretty much spent the whole stream in Lucidcharts today, as much as I actually love Gremlin and graph databases, I think they're so fun and interesting. I'm okay with the fact that we spent the time in Lucidcharts because, again, as I was saying before, we really built up a lot of like how this all works and where it's going. And I kind of think we needed that groundwork, if you will, right, to kind of set us up for where we're going next week. And this is actually one of the most interesting problems I think we've looked at so far. Like, it has so many neat applications and it's so relevant. You know, Frank, you're watching Frank on there too. I know talking to our friend Frank, who's been, I think, following us since day one, right? And looking at some of the space that he is in and these other problems that we've looked at, I feel like this applies to so many things and will be really useful for a lot of folks. So I am excited to see what this where we go with this next week.
Awesome. We will get there. Great. So see you next week. Looking forward to it.
Yeah.
Thank you guys so much for the live stream.
And thank you again for joining us on another episode of the Graph Data and Code Show. We'll be back next week, and we'll actually do traversals next time.
Awesome.
All right, see you guys.
Stay connected, everybody.
Oh, that's funny. We have a tagline now.
It's bad.
See ya.